Everybody sees the slide?
Yep.
Perfect. So thank you very much, Patrick, for this invitation to this seminar. So today I'm going to talk about graph associahedra. And this is a joint work with my friends Lionel, Pournin, and Mario Valencia-Pabon from Paris, France. So this is going to be, so there's this generic idea in combinatorics known as flip graphs. So you have a family of combinatorial objects and some notion of local changes between these, each of these, between pairs of such objects. So for instance, if you got binary strings, then the natural notion of local change or flip is to change one bit, okay? And if you do this, you obtain a graph over all possible bit strings, which is the hypercube in general. So the two-dimensional case being the square illustrated there. You can do the same with permutation and adjacent transpositions. Okay, so you look at all possible permutation, and then you connect pairs of transposition that differ, of permutation, sorry, that differ by a single adjacent transposition. Okay, and then the flip graph that you get is the skeleton of polytope that's known as the permutohedron. Okay, and the two-dimensional version of it being the hexagon. There, so this is the 2D permutohedron on permutations of 3 elements. Now you can do the same kind of things for Catalan objects. For instance, if you pick triangulations of a set of points in convex position in the plane, so triangulation of convex polygons, then you have this notion of flip in which you looked at 2 triangles that form a convex quadrilateral, and then you replace the diagonal by the other diagonal. Okay, so these are called diagonal flips in triangulation. This is also a standard operation, and for triangulation of convex polygons, this gives a flip graph on Catalan objects. So an alternative view, if you know the Catalan bijection between those triangulations and binary trees, for instance, is that, well, flips there correspond to rotations in binary trees. Okay, so now you look at this edge, and instead of this being the parent of the other, you just flip the 2 levels, okay, and you reattach the subtrees accordingly, and you get a rotation between binary trees. Those things are essentially equivalent, and the corresponding flip graph is the famous associahedron. Okay, you can do the same for orientations of graph, for instance, where a flip consists in changing the orientation of one edge. Okay, so there's a theory of those flip graphs that are intimately connected to polyhedral combinatorics on one hand, lattice theory, order theory, because most often those things you can put an order structure on top of them, where you have a top object and a bottom object, and sometimes this partial order is a lattice and so on. So lots of things, lots of combinatorics derive from this notion of local flips. And well, the most standard one, and the one classical one, and the one we'll start with is the associahedra. So let me give you a little more background on associahedra. So this polytope has a long history, right? It goes back to the 50s with Tamari and then Jim Stasheff. It's also called Stasheff polytopes. Geometric realizations have been given by Lee and Laudet also more recently. There's a lot of papers and studies on the various ways to represent those things geometrically in space. Well, how is it defined? So one way to define this is look at a convex polygon, the size of which will define the dimension of the associahedron, and look at the sets of non-crossing diagonals of this convex polygon. So you could connect 2 vertices, and as long as those things are not crossing, well, you have subsets of those diagonals, and the inclusion order of those define the face lattice of the associahedron. Okay, so this is the way to define. And now, if you look at vertices, these are the dimension 0 faces, which are the maximal subsets of non-crossing diagonals, which are exactly the triangulations of the convex polygon. And again, as I said, in bijection with binary search trees, rooted, oriented binary trees, and parenthesized expression, and so on. So, and then the notion of flip, as I said, is there's this quadrilateral diagonal flip in the triangulation that corresponds to a rotation in the binary tree. So, okay, this is very easy, but there's a nice sort of depiction of the Catalan objects that I want to show you before going to this generalization to associahedra of graphs. Okay, So those binary trees, these Catalan objects that are from the vertices of the associahedron, they can be interpreted as syntactic trees of expression. For instance, you want to multiply for terms, for things, A, B, C, D, okay? And the nodes correspond to the operation, maybe multiplication. And the Catalan objects correspond to ways of, via the associativity rule, put parentheses around this product. So for instance, this pair of parentheses, AB on one side and then CD on the other side, gives this binary tree, okay? This is a syntactic tree of this expression, okay? And these are the internal nodes, okay? So I just removed the leap. So it's really a binary tree on 3 nodes. And what I did on the right column there is to circle the subtrees of this binary tree, okay? So the whole tree is a subtree, and then you have 2 subtrees of size 1 there, the pink and the green subtree, okay? Now, if you do a flip in this binary tree, this is in this, in this subject, this is a rotation in the binary tree, and this corresponds to changing the position of one pair of parentheses. So instead of AB on one side and CD on the other side, you multiply A on the left by B and then CD, okay? So you have 2 pairs of parentheses, and now one is nested in the other. This is a rotation in this binary tree. And now there's one subtree that changed. The pink subtree is not a singleton anymore, but it's the rightmost pair of nodes there on the binary tree, okay? So you have this depiction of the binary tree and what we'll call later tubings, okay? You just look at the subtrees of the binary tree. So one question that was studied, and there's this classical paper from 1988, is what is the maximum rotation distance between 2 binary trees? What is the diameter of the associahedron? Okay, so the diameter there meaning what is the longest shortest path, where shortest path is a path along the edges of the associahedron between 2 vertices. Okay, so you want to ask what is the maximum cost of reconfiguring one tree into the another? What is the maximum rotation distance between 2 binary trees of the same side, between the 2 corresponding vertices of the associahedron? And so this seems like, you know, rather elementary problem, but it took really a long time to nail down the exact expression for this diameter. And in this famous paper from Slater and Tarjan and Thurston, so Slater and Tarjan were motivated by application to data structure. They're computer scientists. They invented the splay tree, many data structures, and they were interested in the cost of these data structures, like how many rotations you have to do to access, you know, the elements stored in a binary search tree. This was their motivation, and they collaborated with Thurston, the famous mathematician, who, you know, brought into this business the idea of using hyperbolic geometry to give tight bounds on the diameter of the associahedron. So they showed that it was exactly 2n minus 6 for sufficiently large n, where n here in my setting is, I mean, here n would be 3. Okay, so that would be the number of internal nodes of the binary tree.
Can I quickly ask, Sean, how large is sufficiently large?
It was very large.
Okay.
Okay, and then they asked it wasn't completely satisfying, and they asked this open problem at the end of nailing down the exact value for every n, essentially, right? And maybe have a proof that is maybe somehow more combinatorial, and we're not forced to use this whole hyperbolic geometry business, which is very nice, but also sound like overkill compared to what was really needed. And actually, this was done, you know, rather recently by Lionel Pournin, so who's one of the co-authors in the current work, and he showed that it was true for all n at least 10, right? And then you have specific values for smaller values of n. So, and this took, I mean, this is still quite a bit of work. Okay, this is already not obvious. So what we'll do now is to try to generalize this notion of binary tree and associahedra to a graph theoretic setting. And for this, I need to define elimination trees on graphs. So let me do this now. What's an elimination tree on a graph G? So you take let's pick a simple honest graph, so simple connected graph G. And an elimination tree on the graph is constructed like this. You pick a root, and that's any vertex of the graph. Okay, you call it R. This will be the root of your elimination tree. Okay. Now, you look at what are the connected components of the graph when you remove this vertex. So G minus R, you look at G minus R, you look at the connected components of G minus R, and you just recurse, meaning you compute an elimination tree on each of those connected components, and you attach these as subtrees of the root. Okay, and you can pick any root you want in the corresponding connected components. Okay, so here's an example. You have a graph there on the left, and well, the whole and I'm drawing those tubes already that I showed before, and so the whole set of vertices will be a subtree of the elimination tree that we will construct. Okay, so this is a blue bubble. And then we'll pick a root. So what root are we going to pick? Let's say that A will form a root. Okay, so we pick this vertex A there, make it the root of our elimination tree. And then how many connected components are we left, in G minus A? There's 3 connected components. Okay, 2 singletons, C and D, and then G, B, E, F. Okay, so these will be in the subtree, in 3 distinct subtrees of the elimination tree. Those subtrees are not ordered. Okay, so the siblings of a node are not ordered. So there's no leftmost, rightmost, middle. I mean, it's just in any order. So C and D we're done. So it remains to recurse on B, E, F, G. Right, so we pick a root there, and maybe it can be B, and then this leaves out 3 connected components. And here's an example of elimination tree on this graph. Okay, is that clear? And okay, so why do we do that? What does it mean? What does it capture? It's been defined by several people in many different contexts and different ways. This gives rise to a generalization of the associahedra. Okay, so look at the subtrees that I've circled there. This is called this collection of subset of the vertices. They each induce a connected subgraph because they're connected components at every step. Okay, and remark that either if you pick any 2 of them, any 2 subtrees, either they're nested, okay, one is contained in the other, okay, or they're separated by a root somewhere, okay. So if you pick their union, it is not connected, okay, and I call those non-adjacent. So every tube there, every subset is either nested or non-adjacent, meaning their union doesn't form a connected graph of G, okay? And now if you look at all those subsets, those collections of subsets of the graph that form a connected subgraph and that are either nested or non-adjacent, these are called tubings. And if you look at the inclusion lattice of those, this defines a polytope. Okay, so this is the definition, the combinatorial definition of the faces of the graph associahedron. Okay, so just pick the inclusion order of those subsets of inducing connected subgraphs that are pairwise either nested or non-adjacent, and this is the definition of the graph associahedron. And now, same thing as for the diagonals, right? Now the faces of dimension 0, which are the vertices of this polytope, are the maximal tubings. Okay, it's those tubings in which you cannot add a subset without violating either the nested or the non-adjacent property. Okay, and those are actually in bijection with the elimination trees. Okay, and those form the vertices of the graph associahedron. So just as in the standard associahedron, the vertices were the binary trees, here the vertices of this graph associahedron are the elimination trees on the graph G. Is that clear? And now the nice thing is that we also have a notion of flips or rotation, right? We can define in an elimination tree a notion of rotation, just as we did for binary tree. And this will correspond in the corresponding tubing, in the tubing corresponding to the elimination tree, in removing one tube, so removing one subset, maybe the blue one there, and replacing it by another. And actually, when you remove one such subset, there's only one way to replace it by something else. And this corresponds exactly to the rotation between the 2 corresponding elimination trees. Okay, so here, for instance, on the elimination tree on the left, we are going to do a rotation around the edge AB of this tree, meaning that B will be eliminated before A. Okay, and this will have the effect that the tube containing B, E, F, G will be replaced by the tube containing A, C, D, E, F. Okay, so I'm not proving this. No, I mean, it's a bit technical. So I ask you to believe me that those two operations are actually one-to-one, that you can replace a tube, one of those subsets that need to be nested on an adjacent pairwise by another. This corresponds to doing some kind of rotation in the elimination tree, which corresponds to switching the order, the elimination order of two successive vertices in an elimination tree. Okay, and now, so okay, why do we want to do this? First, it covers it's part of the family of those generalized permutohedra that admit many interesting polytopes as special cases. Okay, so one thing is, if G is a path, then we get the associahedron back. Okay, now think as what is an elimination tree on a path? You pick a vertex, put it at the root. How many connected components do you have? At most two, the left path and the right path. The left, I mean the left parts, right? And what's on the left of the vertex you just removed, and what's on the right, okay? And these are your left and right subtrees in that case, okay? And then you just recurse on those. So this is binary tree. So the special case of the associahedron, you get it back by letting G be a simple path on n vertices, okay? What happens when the graph G, this is the middle picture, is a complete graph? Well, there, whenever you remove a vertex, what remains is a single connected component. You will never disconnect the graph, right? It's complete. So the elimination trees there are one-to-one with permutations of the vertices, okay? And the polytope you get back, if you look at the definition, you get the permutohedron back, okay? So permutohedron is a special case of a graph associahedron when the graph is complete. Associahedron is a special case when the graph is a path. And there's a name for the one that you get when G is a star. Okay, and it's called the stellohedra. Okay, so we'll come back to this one. So nice, special cases. And yeah, so what the diameter of the permutohedron is n squared. The diameter of the associahedron is roughly 2n. We saw this. The diameter of the stellohedron will turn to be 2n. So we'll look at the diameter of those things. But before that, let me hint at some connections between some things that are known in computer science and math that are very much connected to these notion of elimination trees and associahedra. The tree depth of a graph is the smallest height of an elimination tree. Okay, so this is a structural parameter that has been considered by people in the graph theory community. Is if you eliminate vertices like this, split and connected component recurs, what's the minimum height? If you do this in parallel, suppose, then how many steps does it take? In the worst case, this is called the tree depth. Is something that is very much connected to this sort of orthogonal notion of treewidth, and that has been studied separately. And it somehow measures how close is the graph to a star, while the treewidth would measure how close the graph is the graph to a tree. Okay, and this sort of measure intuitively it would measure the distance to being a star. And there's a lot of different concepts and notions that have been studied in combinatorial optimization, approximation algorithm, and graph theory that are very much related to this. For instance, vertex rankings and centered colorings essentially are measuring something that is related to tree depth, which is somehow related to those minimum height elimination trees. Another motivation for looking at those is the fact that it's been successfully applied in this generalized version to the design of data structures. So we remember I told you that Slater and Targent, they were interested in the diameter of the associahedron because they were looking at binary search trees, like data structures for finding, retrieving items in a dictionary. And we can actually use elimination trees on graphs to design data structures that search now not a linearly ordered universe, but what we did with Gilles Bose, John Iacono, Koumoutos, and Langerman in Brussels is to extend the notion of binary search tree to universes which are tree ordered. Okay, so there's not a smaller element and a larger element. They're not pairwise compatible, but somehow they live on its tree structured space. And you can somehow generalize this notion of binary search tree to search trees on trees. And we designed a competitive algorithm that actually the competitive factor is the same as the best known one for binary search trees for trees on trees. Okay, and there we needed structural results on those tree associahedra. In particular, the fact that the diameter is such and such was actually important in understanding how to adapt the binary search tree data structures. And little later, Berenson and Kozma in Berlin designed a generalization of splay trees on trees. Okay, so there's already a couple of papers exploiting this generalization to design interesting data structures for those generalized binary search trees. Okay, so the question we looked at now after all those definitions and preliminaries is what is the maximum rotation distance between two elimination trees on a given graph, which is, let's try to find bounds on the diameter of graph associahedra, just like was done for regular associahedra. Now, of course, it's parameterized by a graph, and you have to either fix the graph or fix a family of graphs or fix, a parameter of the graph in order to give interesting bounds, because otherwise you just know that in the worst case, this would be n squared like the permutohedra if the graph is complete, and it's not super interesting. So as a function of the graph or some structural parameter of the graph, what can we say about the diameter of its associahedron? Okay, so there are special cases that have been looked at. So Lionel did this thing on the diameter of the regular associahedron. He also looked at cyclohedra. So I haven't mentioned this yet. Cyclohedra are associahedra of cycles. Okay, if the graph is a cycle, you call it a cyclohedra. It has also a characterization as the polytope associated with some symmetric triangulations of convex polygons. And he showed there that the diameter for an n-vertex cyclohedra was essentially 5n over 2. This is also a more recent work and also a not so obvious proof. Now, together with Stefan Ungermann and Pablo Perez-Lantero, a few years ago, we proved that a tight worst-case bound on the diameter of associahedra of trees. Okay, so this is something that was useful for us in the data structure for search trees on trees, and it was also an open question by Vincent Pilot and Thibault Manville of what was the diameter of those. Was it linear or was it n log n? Okay, essentially it was somewhere in between those two, and we showed that actually it was super linear in the worst case. Okay, so it can be that for some trees, the maximum rotation distance between two elimination trees on this tree is as large as n log n. So strictly more than, strictly super linear. And this is you need an example, right? Because it's the lower bound that was open, and we sort of crafted a little reduction to construct those examples that were, and we now have a tight bound up to a constant factor. Okay, in general, if you just look at the number of edges and vertices of the graph, you have this result. I mentioned this, the upper bound is n choose 2. This is the diameter of the permutohedron. And Manville and Pilot also showed that it was at least the number of edges. Okay, so this is not too difficult to show, but it's somewhere between the number of edges and n squared. Okay, these are sort of the things that were known before. They also show a very interesting property, which is already not obvious, is that the diameter cannot increase when you take a subgraph, basically. And while this might seem sort of innocuous and natural, it is far from obvious, and it's actually something that we will use in some of the proofs. So there's a monotonicity of the diameter undertaking subgraph. Okay, so again, we have to fix families of graph of some parameters to give more refined results. So one intermediate step in our proof is to look at so-called trivially perfect graphs, which have the nice property of having the diameter of the associahedra is essentially proportional to the number of edges, and these will be sort of instrumental in some steps of the proof. We look at the diameter of graph associahedra that have a bounded tree depth and a bounded tree width. Okay, and there the tree depth, as I mentioned, parameter is sort of natural because it measures some parameter of the best. It optimizes. I mean, it's an optimization over elimination trees, right? So it makes sense that you get a bound as a function of this. From this, you get a bound on bounded tree width graph associahedra, diameter of bounded tree width graph associahedra, and we managed to have in some cases exact values for the diameter of associahedra of complete bipartite or complete split graph. Okay, which is the most recent addition to our graph. Any question at this stage? Clear? Thank you. Okay, let's move on then. So trivially perfect graph associahedra. So what's a trivially perfect graph? So it's these are very nice, very structured graph. They have a lot of property. They're perfect and they're trivially so. So you take a tree, okay, a rooted tree, and you just think of it as a partial order, okay, that you know, A is greater in that example than B, C, and D, D is greater than E, is greater than F, G, H, and so on. And then you look at all comparable pairs, meaning you close this tree down, right? You add every edge between two vertices if one is an ancestor of the other in the tree, okay? And this is the definition of a trivially perfect graph. Trivially perfect graph in the order theoretic terminology is the comparability graph of a tree. Okay, you take a tree order and you just look at everything that's comparable, every ancestor descending pair. Okay, so every path now down this tree becomes a clique. Okay. Now there's an alternative definition of the tree depth of a graph, just as maybe you know that the tree width of a graph is the minimum clique number of a caudal supergraph of the graph. So the tree width of G is the minimum clique number of a caudal completion of G. Well, in the same way, the tree depth of G is the minimum clique number of the trivially perfect completion of a trivially perfect completion of G. So you add edges to make the graph trivially perfect, and you add edges in such a way that the clique number is as small as possible, and the resulting graph is trivially perfect. This is a definition of the tree depth, right? And you can think of it, I mean, it's not, yeah, if you think, I mean, it's not hard to show, okay? And the theorem there is that if you have a connected trivially perfect graph with m edges, then the diameter of its associahedron is no more than twice the number of edges, okay?
Can I ask you a short question about this? So
yes.
they're called trivially perfect graph because you said it's trivial that they are perfect.
Yes.
Why is it trivial?
It's so I mean you want to color them efficiently. You want to show that the chromatic number is equal to the clique number and that you can do efficiently. It's a historical denomination, you know.
Okay.
Someone decided that, yeah. I think it could be there are actually different names. I think Mario could give us different names for the same class of graphs. I mean, this is sort of the most common name for this. Yeah, you can call them compatibility graph of trees. You can, I mean, there are other names. Yeah, it's actually easy to show that perfect.
Okay, then I should just think about it a bit more. Okay, thanks.
It's yes. So yeah, so now the diameter for those is at most twice the number of edges. Okay, and so this gives sort of a tight example to the lower bound of Manville and Pilot, right? Remember that Manville and Pilot showed that it was at least the number of edges. The diameter is always at least the number of edges, and this is at most twice the number of edges. So in some sense, this up to a constant up to this factor 2, this is sort of the minimum diameter graphs for a fixed number of edges. Okay, so let me give a quick proof of this. If we have, we pick the tree from which this trivially perfect graph is built, and we can show that every elimination tree can be transformed into that tree, which is also an elimination tree on G, into a number of steps, which is at most the number of edges. Okay. So suppose that this initial graph for which the trivially perfect G is built, suppose it has height k, then we can rotate any elimination tree to this tree in at most m rotations. Okay, and there we do an induction on k. We move the root of S in at most n-1 rotation. That's always possible because every rotation gives, you know, I mean, you rotate with at most as many other vertices. Okay, and then you get the root, and then you recurse on the subtrees. And by induction hypothesis, this recursion on the subtrees, this is also can be done in proportional. In time proportional to the number of edges, right? So you got n-1 plus the sum over each connected component of the number of edges. And this is exactly the number of edges of the initial graph, right? Because you have exactly one edge from the root to everybody else in every subtree by definition of the trivially perfect graph, okay? And now you can rotate any elimination tree in m rotations to this basic tree S, And now you can go to any one in the same number, right? So it's at most twice m. Okay, so this sort of elimination tree S is sort of the hub to which you go, and then you can go to anywhere else from there by just doing the reverse rotation. So this is an outline of the proof that for a trivially perfect graph, the diameter of the associahedron is at most twice the number of edges. So here's another example of interesting graphs, the star. And remember, the corresponding associahedron is called the stelohedron. So let's think a little bit about what are elimination trees on the star. Remember, you pick a vertex, make it the root of a tree. And as long as you pick leaves of the star, nothing, not much happens. There's always one single connected component remaining. And once you take the center, they're all split. You only have singletons. So the elimination trees on the star, they're very simple. They're brooms, right? You eliminate a number of leaves, and then you eliminate the center, and then what remains is just completely disconnected. Okay, so you've got a long handle and then a star at the bottom, and we call these brooms. And somehow, if you would, let us label the leaves here from 1 to n. These objects, and remember the siblings are not ordered, right? The children of a node in an elimination tree are not ordered. So these objects, these brooms, these elimination trees on stars, they are one-to-one, they're in bijection with partial permutation. It's a permutation of a subset of the leaves of the star. And that's all you need to define the elimination tree. Okay, in what order you eliminate this subset in the tree, and then the rest is defined. Okay, so there the vertices of the stelohedron, right, the associahedron of the star, they're one-to-one with partial permutation. So all permutations of all subsets of the leaves of the star, right? And now what are rotations there? A rotation is either permuting two guys in the handle. Okay, so it's either an adjacent transposition in the handle of the broom, or it is one leaf of the broom that comes at the bottom of the handle. Okay, maybe you can rotate C and R here, and you would get the broom A, F, B, C, followed by R, and then D and G disconnected, right? So rotations, so this has a nice interpretation in terms of partial permutation. Either you add a new guy at the end, you eliminate a guy at the end, or you do an adjacent transposition somewhere in the middle. Okay, this is the combinatorics of the skeleton somehow of the stelohedron. And there we can show, thanks to this, and this was hinted at in the previous paper, but somehow only in one direction, that the diameter of the stelohedron is 2 times n. And in particular, these are trivially perfect graphs, right? And there are exactly n-1 edges. So this is a tight bound on the diameter of the stelohedron. Okay, so now parameterized bound. So what can we say about bounded tree depth graph? Actually, the tree depth is, and because it's so, the definition is really natural when you look at such objects, and this is sort of the parameter that, in the worst case, controls the diameter of the associahedron. Okay, so the notation there is we consider a family of graphs. So, for instance, the family of graphs of tree depth, some function of n. Okay, and we pick the maximum over all graphs of a fixed size n. Okay, so this is sort of a worst case bound on the diameter. Okay, and in the worst case, this is and the bound is tight. This is proportional to the tree depth times n. Okay, and then we really see we can interpolate. If the tree depth is constant, then we have a linear diameter. If the tree depth is linear, which is the worst case, we have a quadratic diameter, and we can really have anything in between. Okay, so and we have tagged examples for all ranges of values for the tree depth. Okay, and there's a nice relation between the tree depth and the tree width. So we also have something that is similar up to a log n factor here for the bounded tree width graphs. Okay, so if we consider the family of graphs of tree width at most t, then the diameter of the associahedra is somewhere between, in the worst case, is somewhere between t times n and t times n log n. So up to a log n factor, we got essentially the same estimates. But this is not high. We don't know. At some point, this log n should vanish, right? Because if the tree width becomes linear, then it should be n squared, right? It cannot be more than n squared. So somehow these bounds should be tightened. But I mean, up to a log n factor, we can see that the tree width also, in the worst case, controls the diameter quite finely. So a proof sketch for the tree depth would be as follows. It's 52. Okay, yeah. Maybe I'm going to be a little quicker here. So maybe I'll skip this proof. Yeah, it's okay. It's basically based on the fact on the trivially perfect graph. So we use the tree depth. We use that the definition of the tree depth is, is the clique number of a trivially perfect supergraph, and then we use the 2 times m result for trivially perfect graph. So this uses this previous result on trivially perfect graphs in a quite straightforward way, and then the monotonicity of the diameter and the addition of edges, right? That the diameter can only increase if you add edges, and then we directly get this result. So this is kind of a quick way to get this result, and this result is tied with a simple example, which are k cliques sharing one vertex. And by varying k, you can control the tree depth. It can be essentially anything, any function of n you want, and you get exactly the lower bound, the matching lower bound up to a constant factor. Okay, so this is sort of a tight characterization of the diameter as function of tree depth. So next, we managed to obtain tight estimates for complete split graphs and complete bipartite graphs, complete bipartite and complete split graph. So what are complete split graphs? There are those graphs there's a bipartition on one side of which induces a clique. Okay, so you have a clique on one side, here's the red vertices, and then an independent set on the other side, and a complete graph between them, complete bipartite graph between them. And then you also have those brooms, right? If you eliminate vertices from this graph, well, unless you don't get rid of all the vertices of the clique, what remains is always connected, right? So it's connected unless you get rid of the 3 red vertices, in which case the remaining vertices, the white ones here in the independent set, well, they're all disconnected and form the bottom star of the broom here. So again, we get those brooms, and the corresponding graph associahedra, they sort of interpolate between the stellohedron, which is the case where there's only one red vertex here, and the permutohedron, which is the case where there's only one vertex in the independent set, right? So this would be the complete split graph N1 would be the complete graph, and the complete split graph 1n would be the star. The star has diameter 2n, the permutohedron has diameter essentially n squared, so we can sort of interpolate between those 2 extremes. And so this is the combinatorics of rotation in brooms. Why is it easier to compute those diameters? Somehow because those graphs don't have long induced path. So we sort of don't have the combinatorics of path and the sort of more complicated combinatorics of the original associahedron, right? They're co-graphs. They don't have paths of length greater than 3, essentially. So we have exact values. So these are the values. They're always at most 2 times m. Because they're also trivially perfect graphs. And but here we got, depending on the relation between Q and P, like if the clique is large or small with respect to the independent set, we have different values. So this is 2m minus P choose 2, okay? If Q is sufficiently large, and there's this expression there, so I leave the details out. And we have something that is also, okay, we don't have a complete characterization, but if we look at complete split graphs, so you have 2 independent sets on each side of size P and Q, then we know that if Q is sufficiently large, then the diameter is also exactly 2 times m. Okay, so we also have a tight lower bound in that case, and it's always an upper bound for every complete bipartite graph. Let me say a word, and some of you maybe have heard of this because they were at SWAT this week. This is a paper that was presented recently. So we knew, okay, we know that for graphs of path width 2, okay, which are sort of close to being path, okay, think of thick paths think of pairs of paths that are sort of connected between them. The diameter of the associahedron can be as big as n log n. This is something that we have. And the recent paper I was mentioning is that for caterpillars, which are path with 2 graphs, okay, think of a path with hair, okay, or legs, you know, it's these are the legs of the caterpillar there. Then they gave, so Berenson gave a sort of tight estimate of the diameter of the associahedron using some binary search tree theory, and it's n times the entropy of the leg distribution. So this is a very nice result, I think. You look at, so you can think of these numbers as a distribution on the total number forming, I mean, you can derive a distribution, discrete distribution on the number of vertices of the backbone of the caterpillar. And you take the entropy of this, and this times n is essentially the diameter of the associahedron. And this is tight. So another example also of a recent contribution, and that sort of extend this worst case n log n bound for pathways 2 in a parameterized way. So there are many open problems left. So we don't have a tie bound with respect to treewidth. We know it's n log n for treewidth 1. These are 3 associahedra. We know that it's quadratic for treewidth n. This is the permutohedron. We have this upper bound, which is n times treewidth n log n. Maybe the truth would be something like this: n times treewidth times log of n over treewidth. So that when the treewidth is n, we have log of 1, so log of 2, sorry, which should be 1. So we have n times treewidth when the treewidth is large, and somehow the lower bound would match as well. So that's possibly a conjecture we could make. We have a thought of co-graph associahedra. So many of our examples, trivially perfect, complete bipartite, complete split graphs, they all have diameter at most 2m, and they're all co-graphs. So is it true that every co-graph associahedra they have diameter at most 2m, where m is the number of edges of the co-graph? Thank you very much for your attention.
All right. Thank you very much, Jean, for your talk. Are there any questions? I mean, while people are thinking of their questions, I have one. So, I mean, these associahedra, they're defined in terms of Catalan objects, right? And they're kind of, it's a natural interpretation for any of these Catalan objects. Is there some interpretation of these graph associahedra in terms of other Catalan objects?
So you can think of elimination trees and tubings, right? And I tried to explain them both, like how they were related, like the bijection between them. And these are the two main interpretations that I have for graph associahedra. There's a wider ranging interpretation of a wider family of such polyhedra that are called hypergraphic polytopes. And there's a nice paper from Benedetti, Bergeron, and Machasek not so long ago that provides sort of but it's slightly, it's much more general somehow, but an interpretation in terms of acyclic orientations of hypergraphs. So you can generalize the notion of an orientation to a hypergraph in some natural way, and you can define phase lattices of polyhedra that are derived from acyclic orientation of hypergraphs, and this includes those graph associahedra, but also much more. So yeah, acyclic orientations would be one other family of objects you might be looking at. Okay. Yeah, there are connections to topology, which I'm less comfortable with also.
Any other questions? If not, I just have a second one. Sorry, I find this quite interesting.
Go ahead.
How hard is it to say if a certain polytope is an associahedron of some graph?
So they have a nice structure. It's not too hard. They can, so, okay, I didn't mention this, but you can have realizations of them in terms of Minkowski sums of simplices. And there are also polymetroids. So there are similar definitions. So actually, definitions have been derived in the Combinatorics community and in the combinatorial optimization community of families of polytopes. in the combinatorial optimization community, you're interested in how, how efficiently you can optimize on those. And of course, the whole matroid theory, matroid intersection theory is developed with that in mind, right? What are the polytopes that somehow on which some greedy algorithm work nicely, on which LP behaves so and so, and graph associahedra fall in one of those categories, in which on which it's sort of easy to optimize, and they have nice characterization. So there's a nice characterization of geometric characterization, of matroid polytopes and of polymatroids, and I would bet that it's sort of you could recover if you have maybe there are concise description of graph associahedra in those terms, and you could otherwise, if you're given sort of a V or H description of the associahedron, maybe this would be more challenging. I mean, yeah, I would have to think about it, but somehow they're very nicely structured, and you can find explanations for the structures from other sources and other community of people who look at things in the optimization side. It doesn't really answer your question, but I think an answer could be found probably there.
Yeah, no, I'm happy with the answer. So that's all right. Any other questions or comments or remarks?
Yeah, I have a question.
Go ahead, Mario.
So yeah, what concerning the distance on these graphs?
Oh, yeah. So you mean what precisely?
The complexity of computing the distance of.
Thank you for asking this question.
Yeah.
It's not staged. So there's this. Okay, there's a big open problem in computer science, which is if I give you two binary trees, what is the rotation distance between them? And the question really is, what is the computational complexity of this problem, right? How fast can you decide? Can you find a shortest rotation path between two binary trees or two triangulations of a polygon, right? It's not known to be polynomial. It's not known to be NP hard. Nobody has a clue, right? And you can definitely ask the same question for a graph associahedra on elimination trees on graphs, right? I give you two elimination trees on the same graph. What is the rotation distance between them? How efficiently can you compute that, right? And so I've discussed with several people in workshops about this problem, and I would tend to think that at least for this generalized setting of graph associahedra, the problem is NP hard. It's in NP because you can give a path that has at most n squared, steps, and but really these are, I think, very interesting open problems. Yeah, we have, we have an algorithm. So while writing this paper, Lionel, Mario, and I, we derived a paper for computing distances on the stellohedron. Okay, so we know if we have two brooms on a star, or two partial permutations with these adjacent transposition and adding or removing people at the end, we know how to compute the distance between two of those efficiently. But that's a very special case. That's sort of very far away from you.
So for stellohedron, it's in P.
Yes.
Okay.
Yes, exactly. Yes.
Are there any approximation algorithms known for that problem?
For the regular associahedron, so rotation distance between binary trees, there's a simple 2 approximation algorithm.
Okay.
And that's based on the 2 comes from the 2 times n in the diameter. It's essentially applying the diameter algorithm.
I see. Yeah. Makes sense.
But nothing else is known. Maybe I mean, an approximation result would already be interesting in whatever case. Yeah. And those, diameter, bounds on the diameter versus computational complexity, these are sort of, for me, sister questions that, are interesting to look at in every case. Thank you.
All right. Are there any other questions?
So this is a list of references.
So we don't seem to have any other questions. So let's all thank Jean again for the nice talk and the interesting discussion.